Hello physics students, this is Dr. Brenzi here, and this is the second in a series of videos about Newton's second law and applying it to find forces. So in this second example we have a 5 kilogram block that is pulled across the floor by a rope at a 30-degree angle. The coefficient of kinetic friction is 0.1. What is the acceleration of the block if the tension in the rope is 10 newtons? Okay, so the problem-solving process that I like to use for Newton's second law problems involves first drawing a sketch, then making a free body diagram. Then we want to place the positive y-axis along the normal force, and then we want to break down any forces into x and y components. We want to write Newton's second law for the x and the y-axis separately. And then we're going to come up with a system of equations as a result of that, which we then want to solve. Okay, let's first start off with drawing a sketch. So, I've read the problem thoroughly through once, so this time as I read through it again, if I notice anything important, I'm going to draw it. So, I have a 5 kilogram block. And right away that sounds like important information, so let's draw a 5 kilogram block. And it's being pulled across a floor by a rope at a 30-degree angle. So I imagine there's a floor, and there is a rope that forms a 30-degree angle with the floor, and the 5 kilogram block is being pulled by that rope. The coefficient of kinetic friction is 0.1, which immediately tells me that kinetic friction is important in this problem. So I'm going to write down that coefficient of kinetic friction right underneath the floor there. And I also think it'd be a good idea to remind myself where this coefficient of kinetic friction comes from. It comes from the formula for kinetic friction, which says that kinetic friction force is equal to that coefficient times normal force. I also decided to draw this friction force arrow pointing against the direction of motion because friction acts against the direction of motion. Okay, finally I'm going to read the last sentence. It says, what is the acceleration of the block? So immediately I know I need to find the acceleration of the block if the tension in the rope is 10 newtons. So I'm being given that this tension along the rope is 10 newtons, and I'm being asked to find the acceleration. Okay, let's take this to the next slide, the diagram at least. So I've drawn a sketch. The next step in the process is to draw a free body diagram. Now, a free body diagram involves just a representation of the object we're interested in and the forces acting on that object. So, first of all, we have to figure out what is this block interacting with. Well, it interacts, first of all, with Earth. Earth is pulling it downward. It interacts with the floor. And it also interacts with the rope. So those are the three items it interacts with. What are the forces being produced by those three items? Well, Earth produces a gravitational force. The floor can produce two different types of forces. It first can produce the normal force, but it can also produce kinetic friction. And finally, the rope produces a tension force. So these are the four forces that I want in my free body diagram. And those are the only four forces that should go in my free body diagram. So let's draw a dot to represent the object, the 5 kilogram block. And we know that gravitational force points downward. Normal force, on the other hand, points perpendicular to the surface. We have a horizontal floor, so the normal force will point upward. Friction force We've already identified that acts opposite the direction of motion, and I've drawn this moving toward the right, so friction will be moving toward the left. And tension force points along the direction of the rope, so we're going to draw a tension force that is 30 degrees away from horizontal. Okay, my third step in my process is to draw X and Y axes that will place the normal force on the positive Y axis. So the positive Y axis goes on the normal force. So that's the positive Y direction. On a normal graph, positive X will then point toward the right. And then I can fill in my other two set of axes. Okay, now the next thing we need to do is we need to make sure that all of the forces in my free body diagram are acting along these axes. And if they're not, then I have to break them down so that they are. Well, normal force, friction force, gravitational force, they are all on one of these axes, so I don't need to worry about those. But I do need to worry about this tension force. That's not pointing along either the X or the Y axis by itself, so I need to break it down so that its components do point along the X and the Y axis. So I'm going to create a copy of that vector right down here. Whoops. I got a little ahead of myself there. Sorry about that. And I want to create a component. I want to break it down into a component that goes along the x-axis and a component that goes along the y-axis. And when I do that, what happens is that I end up drawing a right triangle. So this is a right triangle, and the right angle is between the two vector components. And we also know that this angle is 30 degrees. So now I can use some trigonometry to figure out what the vector components have to be. If I want to figure out opposite, well, that involves the hypotenuse and sine. So opposite equals hypotenuse times sine. Hypotenuse times sine. Adjacent. The adjacent side I can get from cosine. So adjacent equals hypotenuse times cosine. So I've now broken down this vector into an x component and a y component. I've run out of room on this slide, but I know I don't need these two things anymore, so I'm going to erase those so that I have a little bit more room here. So I'm just redrawing the free body diagram, just made a copy of it. But I want to replace this with its two components. So let's take it out and replace it with its two components. There we go. Now this is a free body diagram that I can work with when I'm going on to step number 5. This one I could not work with, the one on top. But that one on bottom I can work with. Okay, let's take the sketch and this new diagram over to another slide. So let's redraw that. Here's a sketch. You don't have to worry about drawing this. You have this in your own notes. But I need to draw it here. And this is the brand new free body diagram with the tension force broken down into its x and y components. Okay, step number 5. Now I have to write Newton's second law in the x and the y direction. Normally I have you write x and y side by side, but if I want to do that on this particular slide, I'm not going to have enough room. So I'm just going to look at the x direction and then write the y direction in a little bit. But you can certainly write them side by side if you wish. I would actually advocate for that, but I don't have the room on my slide. Anyway, let's write F net equals ma, and let's consider just the forces acting in the x direction. So I have the x component of the tension force, and pointing in the opposite direction I have friction force. So those two added together make F net, and Newton's second law says that equals mass times acceleration. I know that the tension force is 10 newtons, and I can replace this with this equation right here. And I know the mass of the object, so let's make those three substitutions. So we have 10 times 0.877 minus the coefficient times normal force equals 5 times 8. If I evaluate this, multiply those two together, I get 8.77. And they give me the coefficient of kinetic friction in the problem, so I can replace that. And this is as far as I can get in the x direction. So now let's turn our attention to the y direction and go as far as we could possibly go. So in the y direction, we're going to write Newton's second law, but this time acceleration in the y direction is what we want to use. And the net force comes from only forces in the y direction. So to write F net in the y direction, I need to add up the normal force plus the y component of tension force plus gravitational force, which is pointing downward. So I have normal force plus that x component, or y component, excuse me, of tension force minus gravitational force equals 0. They give me the tension force. I can also write this as m times g, and I know the sine of 30 degrees is 0.5, so let's make those replacements. F net plus 10 times 0.5 minus mg equals 0. Well, I can evaluate this, and I know the mass is 5 kilograms, g is 9.8. Notice I didn't say negative 9.8 because that negative sign means pointing downward, and I've already told this equation that gravitational force is pointing downward, so I don't need another negative. So I have normal force plus 5.0 minus 5 times 9.8 equals 0. I can simplify this. Let's evaluate that. And finally I get normal force minus 44.0 equals 0. Okay. Now I could technically actually solve this for normal force, but I'm going to do that in the next step. Well, what is that next step? Well, we now have a system of equations. We have an equation in y, and we had an equation in x. Those two put together make a system of equations. I'm going to put those on the next slide here. So we're going to solve that system of equations. So what you should have on your paper, at the very bottom of x, you should have 8.77 minus 0.1 times normal force equals 5a. And this is what we have in y. So we have two equations, two unknowns. That makes a system of equations that can be solved. There are two ways that you can solve systems of equations. You can solve them by elimination or by substitution. And it turns out that when I noticed, that two of these, this equation has two variables. This equation only has one variable. So the best method for me to use, the quickest method, is substitution in this case, because I can solve for this normal force and then plug it into this equation, and that will give me acceleration. So let's do that. Turns out normal force is 44 newtons, so let's substitute that into this equation. And when I do, I will get this. Now I can evaluate the left side of that equation. And when I do that, I end up with an acceleration of 0.874 meters per squared second. Okay, so that is how you will work with Newton's second law when you have a force that is not acting in the x or the y direction. You have to be able to break that up into components. Okay, I look forward to seeing you in the next video, and have a good day. Bye.